Okay. Will he come back to say, okay, can I start? He told me you can, wait. He said, okay, yeah, thank you. Okay, so hi everyone. As the chair of this session, it's a pleasure to introduce myself. I'm Thomas Peron, and following the tradition of the event of introducing yourself, I am an assistant professor at the Institute of Mathematics and Computer Science at University of São Paulo. I'm affiliated to the Applied Math and Statistics Department, and although I'm in a math institute, I'm a physicist, so don't tell my department colleagues about this. I think they suspect already. But okay, so this is actually a joint work with Fernando Metz from the Physics Institute of the Federal University of Rio Grande do Sul. It's very sad that he was supposed to be here. He had a talk scheduled for, I think, for Monday. But yeah, so you may know how the situation is in Porto Alegre. The airport is underwater, so he got his flight canceled. But okay, today we'll talk about mean field theory of vector spin models on networks that have an arbitrary structure, and also the spins of these networks will have also an arbitrary dimension. So before I tell you about our results, just let me give a very quick motivation. Yeah, we already seen in this event many talks about synchronization, phase oscillators, Kuramoto model. Guilherme Costa talked about this. We had Joan also, so I don't have to introduce the Kuramoto model. But basically what we have is a set of phase oscillators. The states of these nodes, they are confined into, between 0 and 2 pi. And usually in this context, what we are interested in is to analyze how the order parameter here changes as a function of a coupling strength or other parameters of interest. Here in this talk, we can also, by the way, we can also see these, think of, instead of phase oscillators, but we can think of spins that are confined to rotate on the plane. Actually, the Kuramoto model without natural frequency is equivalent to the XI model in statistical mechanics. So here, we'll release the oscillators from the plane. They will be allowed to rotate on arbitrary dimensions. So in here, and what we'll study here is how the order parameter changes as a function of the coupling strength. But we allow these d-dimensional spins to have an arbitrary network structure. So there is another question within this problem that we want to answer, but I will mention this very soon. Okay, so what is our model? Our model is described by a Hamiltonian. So we have a set of n spins, and each spin has d coordinates. Here, Cij is the network adjacency matrix is 1 if they are connectors, 0 otherwise. And our couplings will be given by this Gij. So we have a ferromagnetic coupling, K0. C is our average degree, so we have normalized coupling. And we also have these interactions. They can be mediated by weighted couplings, which are random variables. They are Gaussian distributed. When our dimension is equal to 1, we have the IC model. When dimension is equal to 2, we have the Kuramoto model, but in this case, without the natural frequencies. And when d is equal to 3, we have the Heisenberg model. And what we want to answer is, we want to know what is the impact of degree fluctuations in the high connectivity regime of this model. But we will be interested in particular in finding if there is a universal behavior when we take the limit of the average degree to infinity. Suppose the following experiment. So suppose we start with a network that has initially a Poisson degree distribution and another network that has another degree distribution, for example, an exponential 1. Now we tend the number of nodes to infinity, and subsequently we tend the average degree to infinity, and then we ask what happens with the magnetization, with the other parameter as a function of the coupling strength. Will we observe some type of universal behavior? In other words, we will see that this magnetization will behave the same in both networks, that's what we want to see in our model. Okay, so, but before that, we need to establish which degree distribution we use. And for that, we'll consider our networks to have a negative binomial degree distribution. Here, K is the number of neighbors, C is the average degree, and alpha controls the network heterogeneity. Why we are using this degree distribution? Because it's very convenient. It has some methodological advantages. When alpha goes to infinity, we have the Poisson degree distribution. We have Erdős-Renyi random graphs. When alpha goes to 0, the variance of the degree distribution diverges. And in between these two extreme cases, we have a very special case, which is the exponential degree distribution. So we can tune our network continuously by changing just one parameter. So this is very convenient. We don't need to change between different configuration models. We just set one degree distribution, we change one parameter, and then we have different network structures. Plus, when in the limit of infinite connectivity, we have just one parameter characterizing our network structure. So it's very convenient to use this type of networks. Okay, so we want to calculate how the magnetization or the order parameter changes as we change the other parameters. So here is a Hamiltonian, the spins, our couplings. And to calculate M, one way to calculate M is to find who are these marginal probabilities of our system. The probability of finding one particular node in one particular spin configuration. And this we find by calculating the marginal probabilities of the Boltzmann factor. So beta is the inverse of the temperature, and H here is our Hamiltonian. And this integral is calculated over this hypersphere and d dimensions. So the whole problem is summarizing and finding which are these probabilities. So I will skip all the lengthy calculations, and I'll go directly to the main result of our paper. So when we take the limit of infinitely many nodes, and then infinity average degree, and by using what we call the cavity method, we are able to show that these probabilities, the probability of finding one spin in a particular configuration is given by this probability, which is proportional to this effective Hamiltonian. We have three terms. The first one measures the alignment of this spin to the global mean field, but this actually is not the actual magnetization. This is what we call the magnetization or the order parameter in the cavity graph. For those familiar with the heterogeneous degree mean field, this is exactly the same order parameter. When you have heterogeneous degree mean field equations, and when you define the order parameter that decouples all those equations, is this one, is the order parameter in the cavity graph. The second one measures the alignment of this spin with this z, which is a Gaussian random vector. And the third one is proportional to the correlation between the components of these spins. Here, G is the rescale degrees, the actual degree divided by the average degree, and nu G is the rescale degree distribution. Okay, so this is our main result. Having this, we can calculate the marginal probabilities and the magnetization. So here we'll focus first on the case where we don't have random interactions, random weighted interactions. We have random interactions of the network. So when K1 is equal to 0, we can calculate the global magnetization on the cavity graph by this equation. We solve this equation in a self-consistent way, and then we insert the result here in the global magnetization. So now we have everything. Notice here that the dimension enters here in these modified Bessel functions. Okay, so now we have everything set, we can start performing some experiments. So although our equations are valid for any dimension, let's focus on our case we know quite well, which is the Kuramoto model. Here, when alpha is infinite, we have that the rescale degree distribution is a delta function at 1, and this corresponds to the case of the fully connected graph, Erdős-Renyi random graphs, and regular graphs. So in this case, we see that the points are simulations, the solid curve are the solutions of these two equations. So for this case, we do have some universal behavior. Fully connected graphs, Erdős-Renyi and regular graphs, they behave equivalently here, because all the points, they collapse on the same curve. But as we decrease alpha, the critical coupling goes to the left. We have synchronization, it starts to emerge sooner. But the total magnetization, the curve of the magnetization bends. So for a long time, I think highly heterogeneous networks were regarded as optimal topologies for the emergence of synchronization, because the critical coupling vanishes as we increase the heterogeneity. But yes, indeed, the critical coupling reduces, but also the magnetization. So the critical coupling goes to 0, but the magnetization goes to 0 when alpha goes to 0. So we don't have a critical coupling, but we don't have magnetization at all. So it's not that optimal in this sense. Okay, so in our calculations, we can calculate the global order parameter. So we have global information of our system, but we also, since we calculate the probabilities, we have local information about the dynamics of the nodes. We can calculate these, the probability of finding a node in a particular spin configuration. But these probabilities, they depend on random parameters, which are G and Z. So we can average this probability over the whole network to find the average probability of finding a node in a certain spin. And the same way we can calculate the average, we can calculate the standard deviation of this probability. So here, when alpha, for the fully connected graph, we see the average here, the line is the average probability calculated by the theory. The red points are the average points of the simulations, and the gray dots are the independent single realizations of the simulations. So we see here that almost, well, so yeah, we have minor outliers here, but all the simulations, they collapse on the same curve. As we decrease alpha, we see that we can have this standard deviation of this probability. We have, this is shown in this shaded area, starts to increase. And then we do start to see some points scattered of this shaded region. And as we decrease alpha, these fluctuations increase, which makes sense with the calculation of the other problem we just did. How much time I have? 2 minutes, okay. So let's summarize everything in this diagram. Here, this equation is the critical coupling for the emergence of synchronization. We see here that depends on dimension and the variance of the degree distribution. Here's the paramagnetic is the asynchronous phase, and here the synchronous phase, the ferromagnetic one. And if we construct a thought experiment, for example, let's say we want to have a particular critical coupling in our network, we can have the same value by tuning these parameters, the dimension and the variance of the degree distribution. We can balance the effect of the dimension and the variance by controlling them to have the same critical coupling. And one interesting thing that we saw is that when the coupling is much larger than 1, we can expand the other parameter, and we found these dual functional forms for the other parameter. So between 0 and 1, this order parameter behaves 1 over k0 to the power of alpha. But after alpha, when alpha is larger than 1, this dependence vanishes. So we can use this as a kind of way to classify networks in terms of their dynamical behavior. So we also generalized the Sherrington-Kirkpatrick model for heterogeneous networks, but I will skip this. There are many details here you can see in our paper that was published 2 years ago, and I'll leave just answering the question, is there a universal behavior when the average degree goes to infinity? It's not universal for a heterogeneous network, but for the definition of heterogeneous network we use in this work. So I'll leave for some time for questions. So.
Questions? People are getting tired, right?
Yeah, spin models at the end of the day. Okay, I'll give you that.
Okay, one question there. Okay.
Thank you. Thank you. For me, it's very nice, the presentation, because this is my topic.
Oh, cool.
I see that in physics, but what is the meaning here? Is out of physics? The model is implemented in other aspects?
I think I didn't understand your question.
For example, here you have spins and coupling. This means this is ferromagnetic.
Yeah.
Or, for example, you have dipolar interactions. Yeah. But
Okay.
here, what is the meaning for other networks, for example? It's possible that one node, the behavior is like a spin. You understand?
Yes, you're saying what is the type of interactions we have on our network?
Yeah, but more than that, it's possible to apply this physics in networks, difference to materials, difference to magnetic materials. Yeah.
Oh, okay. If this is...
Yeah, I think it means if there is a physical system that would...
okay. If there is a physical
realization of this system, yeah.
If there is a physical realization of this system. Very good question. I don't know. I really don't know. I'm sorry. But yeah, I don't know. If there is a physical realization, I don't know. I really would like to answer your question, but perhaps a Dilson motor can come up with some weird solid material that that has those properties. He was talking about this on Monday, but yeah, unfortunately, I don't know.
Okay. Any other questions? Okay, so thank you, Thomas.
Yeah, thank you.
And I'll give you back